So I just wanted to brief the car bumpers problem. So remember that problem, if 5 cars are lined up literally bumper to bumper, how many bumpers are touching? So remember Polya's 4-step problem solving process. The first step is understanding the problem. The biggest issue I saw here was people forgetting how many bumpers a car has, and telling me that there were 4 points of contact, so 4 bumpers. But in fact, cars have bumpers on the front and the back, so at each point of contact there were 2 bumpers touching. I didn't see many other confusing things that people turned in. The only other one that I noticed or someone asked me about was, what do you mean by lined up? Could that line be a circle? And well, I think that there is some room for interpretation of that. Really, I think line means, like, if I think of cars lined up or people lined up, I don't think of them standing in a circle. I think of them in a straight line. So certainly that's a question that could be asked here, but the real key to this problem is thinking, where are the bumpers? What does it mean for bumpers to be touching? Hopefully you watched a video where I solved this. Here's my terrible picture that I drew. So my heuristic was to draw a picture. That was also the most popular heuristic that my students used for this problem. So here's some pictures that they drew. Some other heuristics that people used, oh wait, before I get to those, so here's the crummy picture I drew. Here's another picture I drew. Notice the difference between these two. Although the top one is crummy, it does have the cars labeled. It shows the bumpers, which are the important part of this question, and it shows that there are 2 bumpers touching in each spot. The bottom picture doesn't really show any of those things. It just seems to be amorphous circle blobs. Now, I believe that you could solve this problem by drawing the bottom picture. However, if the problem were any more complicated or you were trying to explain it to someone else, looking at the bottom picture, I would need to know what problem I was talking about before I could remember even what I was doing with those circles. Whereas in the top picture, I can probably remember, oh yeah, the bumpers are there, so this was that bumper question. Just adding a few words, even to a crummy picture like my top one, can really help it stand out and be clear what you're doing. Okay, here are some other heuristics. Some of my students mixed a picture and deductive reasoning, but this can certainly be done just using deductive reasoning. So I'll say what's here. So 5 cars times 2 bumpers each is 10 total bumpers. The very first bumper and the very last bumper do not touch anything. 10 minus 2 gives you 8 touching bumpers. There's deductive reasoning. I also had a student use manipulatives. Here's the picture he sent me. He took some guitar picks and lined them up front to back, bumper to bumper, letting them represent cars, and then just counted up all of the sides that were touching each other to get the 8. Now, so remember Polya's last step. Look back and examine the answer. Can you check the result? Does your result make sense? Can you check the argument? So if you drew a picture, if you look at that picture, can you see clearly the 8 bumpers that we're touching? Can you derive the result in a different way? Can you reason it out if you drew a picture? Or could you draw a picture if you reasoned it out? Can you see the solution at a glance? Once you've solved the problem, can you tell immediately what the answer is? Can you tell how you got there? Could you use this on any other problems? Have you learned anything new? I'm going to look at that bottom piece of, can you use this result or method on other problems for a minute here? So if 8 cars are lined up literally bumper to bumper, how many bumpers are touching? Okay, to solve this problem, we could draw 8 cars. We could do that deductive reasoning and take 8 times 2 and then subtract the front and the back one. What if 10 cars are lined up bumper to bumper? How many bumpers are touching? Okay, again, we could do that same thing to get this answer. If n cars are lined up literally bumper to bumper, how many bumpers are touching? Okay, for this one, drawing a picture is harder. So if we have our n cars, then I guess we could count up the bumpers that we're touching there. It's a little harder to see what the solution is going to be there, but you should be able to reason this problem out if you understood the first one that we did. If we have some cars lined up bumper to bumper, and there are 46 bumpers touching, how many cars were lined up? Okay, we should be able to solve this problem if we understand our solution to the first one. Okay, if we really look back and think about it, we should be able to do this. 20 children are playing Red Rover. One of the teams has 13 children on it. How many hands are touching when they're lined up? Okay, if you know the game Red Rover, I don't know if they play Red Rover anymore. It's kind of a violent deal, but if you play Red Rover, this game is this problem is very, very similar to the one that I asked you already. A doubly linked list has 12 elements. How many non-null pointers does it contain? Okay, this question is just like the one that we talked about. Okay, so if you know what a doubly linked list is, that's a list where you have a pointer both to the preceding element and the following element. So each item has 2 links. The first item only has a link coming in the first item is the start of the list, so the start is there, but its pointer backward is null, and the last item's pointer forward is null. So that's a problem that we could attack, or could at least think about in terms of the problem we did. What if I want to build a ladder ball set out of PVC pipe? How many ends of PVC pipe will you need to prime and glue? Okay, is this question like our question? Does this question have similarities to our question? Could we use what we learned from our question to attack a question like this? Okay, so the point of this, remember, solving the problem isn't the last step. Looking back and examining the answer is. And the real reason is we get something out of solving problems. Every new problem you solve will make you better at problem solving, especially if you take the time to stop, look back, and examine your solution. Because the more problems you've seen, the more problems you remember how to do, the more problems you can look at later and say, wait, I've done something like this. Let me try that same technique.